All right, well, hello AP Physics students, and welcome to this video lecture that's going to introduce us more formally to conservation momentum. Whether indirectly in that pivot interactive that we did, or directly on Friday with that visual collisions lab, we started working with conservation momentum, but I want us to understand a little bit deeper as to what it is and what it's all about. So with conservation momentum, we're always working with some type of collision, okay, whether it's an inelastic collision or an elastic collision like you worked with on Friday. So I have a collision going on within this first slide here. So we have two objects that are both traveling towards one another. Okay, so I'm kind of showing you three different snapshots here. First, they're traveling towards one another, so you can see their initial velocities. And then second, this is the collision itself. Okay, we can just say that it's a elastic collision here. So I'm showing you the forces that each ball is applying on the other. And then finally, we're seeing these two balls or scientific spheres then moving away from one another. And I actually have this one labeled wrong now that I'm looking at this. This is V final 1. So what we're going to do from here is we're going to write impulse momentum theorem equations for each of the objects that we have represented here. So the form that takes, remember, is we're just basically combining our two definitions for change in momentum, where we say that force times time equals mass times a change in velocity. So starting with object 1, the force that we see in the second snapshot acting on object 1 is F21 times time, and that's going to equal then M1 V final 1 minus M1 V initial 1. Okay, so really all I'm doing there is I just distributed this mass out to our change in velocity. Remember, change in velocity is always final minus initial. Okay, moving on. So for 2 then, it's just going to be the exact opposite. So it's going to be force of F1 on 2 times time, and then that's going to equal M2 V final 2 minus M2 V initial 2. Okay, so what I'm going to do from here then is I am going to just add these two equations up. So what that's going to give me then is I'm going to have F21 plus F12, and those are going to be multiplied by the time, and then I'm going to have M1 V final 1 plus M2 V final 2 minus M1 V initial 1 plus M2 V initial 2. Okay, so what we're doing here is we're taking a look at this system as a whole, where we're seeing the impulse. So this was breaking down the impulse that each was experiencing individually, and now we've kind of just combined all that together. Now, this whole big thing here we can simplify if we think about conceptually what's going on with these internal forces, okay, these forces that object 1 and 2 are applying on one another. F21 is pointing to the left. We typically take the left as as negative, and F12 is pointing to the right. We take that as positive. Now, remember in Newton's third law that these forces are actually equal to one another. So what does that mean right here? Well, that means that these sum to 0. So now, what is this actually going to look like? Well, this is going to look like 0 equals momentum final minus momentum initial. If I simplify that down, we get our definition of conservation of momentum, okay, where we're saying that our initial amount of momentum within a system is equal to that final amount. Now, this only holds This only holds when we have a closed system, where the only forces that we are worrying about are these internal forces, or the forces that these objects apply to one another. If we have a closed system, that changes things pretty drastically. This is not going to always be true if we have an open system, because then we actually have to worry about external forces like friction, okay? If that's the case, we can analyze that, but this big long equation here gets extended out, and we would actually have to include external forces in relation to time. Now, I want us to understand a little bit more conceptually about what's going on with conservation of momentum. All right? What we're saying here, knowing that these forces are equal to one another, we're saying that the impulse that each object within this collision experiences is the same. They're experiencing the same magnitude of impulse, the same magnitude in their change in momentum. But what's different? Well, depending on the mass of these objects, what's different is their change in velocity. That final velocity after the collision is what ends up being different. Okay, and we can kind of relate back to Newton's third law when we think about this, right? Like, we know that the forces in an interaction are equal, but what could be different? Well, the acceleration could be different based on the different masses we have within that interaction. So I want you to see the connection between conservation of momentum here and Newton's third law, because it can help us analyze these situations and kind of predict what might be going on after a collision happens. All right, so this is your conceptual sort of mathematical intro to conservation of momentum, just kind of debriefing the things that you saw within those labs that we did last week. Now, when you start problem solving with this, keep this simple picture in mind right here. Remember, you're summing up all of the momentum that you have initially within a system, and that needs to equal the sum of all the momentums you have finally. Okay? So keep that in mind. Extend it out. It's going to be a long, kind of messy looking thing, but we need to keep all momentums initial and all momentums final separate. So you're going to get some practice with that now, working through some problems. I'll have the answers posted for you next to the problems. If you don't get the correct answer, feel free to talk with another group or even mark that, and maybe we can go back to that and then kind of debrief those problems tomorrow in class. So take care, physics students. We'll see you tomorrow.